We have seen earlier also that the total response can be split into two parts, transient response and steady state response. If we apply a sinusoidal input to a system, then the transient part of the response dies out with time. For example, consider a random output signal equal to 6 plus Euler's number raised to the exponential minus 5t. Now, if we have to find the final value, then you can clearly say the term consisting of Euler's number raised to the power minus 5t will die out when t tends to infinity, whereas 6 will remain as it is. So, the transient part of this response is equal to Euler's number raised to the exponential minus 5t multiplied by unit step signal, whereas the steady state part is equal to 6 multiplied by unit step signal. Transient response actually dies out for all inputs even if the input is not a sinusoidal signal. But we have a special property with respect to steady state output, which is if the input is of sinusoidal nature, then the steady state output will also come out in a sinusoidal form. The system may provide a phase shift as well as a change in the amplitude, but still, general form of the steady state response will be of sinusoidal nature. The magnitude provided by the transfer function is equal to the magnitude of the transfer function, putting the value of s equal to j omega. We have discussed in the first chapter also that for sinusoidal input we put the value of Laplace variable s equal to j omega by completely ignoring the damping factor. The same way we can find the phase shift provided by the system. Here omega is the angular frequency of the input signal. Try to solve a question, you will get more clarity of the concepts. Now let us see the solution. Input is provided to be equal to cos 2t multiplied by unit step signal, whereas the transfer function of the system is provided in frequency domain, which is equal to 1 upon s plus 1. Your first step should be to convert the input signal from time domain into frequency domain. The unilateral Laplace transform of cos 2t multiplied by unit step signal is equal to s divided by s square plus 4. We also know the response is equal to transient response plus steady state response. The Laplace transform of the output is equal to Laplace transform of the input multiplied by transfer function of the system. We can easily find the Laplace transform of the output, but to find output in time domain, we have to use partial fraction method so that this expression can be converted into Laplace transform of some basic signals. Using partial fraction method, we first have to find the values of the coefficients a, b and c. For doing that, we have to compare the rightmost equation with the leftmost equation. It will be better if we multiply the terms in the left hand side expression. Now we have to simply compare the leftmost equation to the rightmost equation. By comparing the coefficient of s square, we will get a plus c is equal to 0. Similarly, by comparing the coefficient of s, we will get a plus b equal to 1, and the same way we will get 4c plus b equals to 0. We have 3 equations and 3 variables. Solving these equations, we will get the value of a equal to 1 by 5, b equal to 4 by 5 and c equal to minus 1 by 5. Now we have to simply put these values in the equation so that the expression of output signal get factored into Laplace transform of some basic signals. After taking inverse Laplace transform, we will get the output in time domain to be equal to cos 2t plus 2 multiplied by sin 2t minus Euler's number raised to the power minus t multiplied by unit step signal, the whole being divided by 5. Now, to find the transient response and steady state response, we have to put the limiting value of time when it tends to infinity. Sinusoidal signals don't have any finite value, as they are purely oscillatory functions whose value continuously oscillates between its maxima and minima value. But the expression Euler's number raised to the power minus t divided by 5 will die out when time tends to infinity. So the steady state response is equal to cos 2t plus 2 multiplied by sin 2t divided by 5, the whole being multiplied by unit step signal, whereas the transient part of the output is minus Euler's number raised to the power minus t multiplied by unit step signal divided by 5. For the third part, where we have to find the magnitude and phase shift provided by the system, we have to simplify the expression of steady state response by first taking 1 by root 5, a common term, out of the expression, and then assuming cos theta equal to 1 by root 5. This assumption step is actually the most important step, which comes only through practice, and I will tell you later why I have taken cos theta equal to 1 by root 5. As a matter of fact, it is not a fixed step. You can also take sin theta equal to 1 by root 5, but by doing that, you will increase few more steps in your solution. Well, anyways, the steady state response can be written like 1 divided by root 5 into cos theta multiplied by cos 2t plus sin theta multiplied by sin 2t. Here theta is equal to tan inverse of 2. Now we have to use a very simple trigonometric identity, which is cos a minus v equal to cos a cos v plus sin a sin v. This is the reason why I have considered cos theta equal to 1 by root 5. The only reason being that if I have taken sin theta equal to 1 by root 5, then the final expression would come in terms of sin theta. But since the input is taken in terms of cos theta, I wanted to convert the expression of steady state response in cos terms only. That's why I have taken cos theta equal to 1 by root 5. I hope you are getting my point. By applying this trigonometric identity, you will get the steady state response equal to cos 2t minus theta divided by under root 5. By comparing the steady state response with input signal, we can easily find the magnitude introduced by the transfer function is equal to 1 by root 5, and the phase shift provided by the system is equal to minus tan inverse of 2. This is one way you can find the phase shift and magnitude, but there is another way which I discussed initially and is actually quite straightforward. You have to simply put the value of S equal to j omega, where omega is the input angular frequency, in the equation of the transfer function, and by finding the transfer function's magnitude and phase shift, you can easily find value of the magnitude and phase shift provided by the system to the steady state response.